So,
Hi, Serena. How are you?
so this is the merged link. Okay, great.
Yeah, so first is the synaptic plasticity paper, and then the other paper he also said we could add that.
Okay, I'll ask him what order he wants to do things.
Oh, I also told him about the general question. So yeah, if by then hopefully, oh, Jamie's here. He can ask the general how he became a scientist question.
Sorry, hello everybody. I got a notification just in a second. Could you hear me, or have I been kicked out?
Yeah, I can hear you.
Oh, okay. Right.
Are you
I
able
know.
to ask the general question today?
Absolutely. Yep, I can
Okay,
handle that. Yep.
great. I think this is going to be really cool. I'm excited about the non-von Neumann new physical devices that do these things. I hope this is an industry trend that really catches on.
Yeah, I agree. I think this is the way we can maybe actually generate real AGI by having this physical synaptic plasticity, like in the physical device integrated. I think that's the way to go. I agree.
It is. I will refrain from launching into astrocytes though.
Oh, that we make astrocytes?
Well, yeah. What it's going to be
And,
how are we going to set up resonances and calcium waves and get theta waves and stuff?
and the immune system, the artificial one. So yeah, I agree.
I think we'll get there. That'll just have to be next. But once we're cooking physical devices that have these three factors, plasticities and things, then, we'll discover those limitations, and lo and behold, it'll be astrocyte networks.
I'm starting to get quite fascinated by neuroplasticity. Ever since you've been talking about it, and ever since it keeps coming up in these rooms, I've been like, this is fascinating. So that he's talking about doing this in computers, right? Like using the methods of neuroplasticity to help
Well,
computer.
we've been doing them on classical computers with mathematical algorithms. What we'll hear about today is how we're starting to make physical devices that have more natural physical properties that we can exploit that make better models for what we've explored mathematically. So it's exciting in the sense that if there's an industry trend and they start cranking these things out, we can just get to that next level in performance and see what stops us then.
That is so awesome. That is so cool.
It really is.
Also for implants, don't you think? Like to have the chip implants that have this would make the implants way better.
Yeah, if we can have, for example, implants that have pre-learned complex behaviors that just need that final step of wiring in an organic sense post-transplant, that could get really interesting.
That sounds as exciting as it sounds scary as well.
Oh, what could go wrong?
Yeah, nothing, right?
Right. Insert decades of sci-fi literature.
Absolutely. It's like all of these people, like, we were right all along. Um, I wonder if there'd be ways to like put information on this. You know, like if you ever got like a tutor program that knew how to play piano and then could like adapt how you play to how it taught you or something awesome like that.
I suppose in principle, because it is a mapping of, intents of notes to actions
Mm-hmm.
that needs to be trained to be precise.
Mm-hmm. And so if it had all the information already in it, like you just said, right? Already sort of pre-programmed in, but then the neuroplasticity would come in with the human maybe finding certain hand motions that the left hand motion more difficult than the right, and it would then conform the regime, the
Well,
teaching.
the tricky thing on that kind of stuff is that it can't be too automatic, or there's no way to, put in stylistic variations. You somehow would have to map it to intent, but the, but the person needs to sort of, express themselves through the subtle variations.
Yeah. Yeah, like in the way that like everybody can play Bach or something. Well, not everybody, but people play Bach, but everybody seems to have a very subtle sort of accent to how they play, right?
Hmm.
It's not just completely duplicated.
Yeah, and then that stylistic and variation is what makes it special. Certainly for repeat performances where you want to hear it again, but you want to hear it in a particular style.
Or for the person playing it or something like that, right? Yeah.
Hmm.
Oh.
Yeah, so just to hi Wisdom, how are you? Hi. Um,
Hey,
uh,
Wisdom.
our guest speaker arrived. Welcome, Dr. Ghazi Sarwat. Um,
Thank you.
thank you
Hi.
for
Welcome.
coming. uh,
Thank you for
well, what?
inviting me. Yeah.
Yeah, thank you. It's wonderful to have you. We were already talking, very excited, like about your work. We couldn't.
Oh, that's great. I missed it. Okay, perfect. I hope I can justify my presence today.
Oh yeah.
Oh,
Oh,
certainly,
no
certainly.
doubt.
No, I was pointing out it's just such an exciting trend that we're getting to physical devices that have a non-von Neumann approach to implementing these things we've had to study with mathematical models. But it's just an exciting trend. Look forward to much more.
Absolutely. Absolutely. It's a very brave world.
Okay, we'll start in a couple more minutes, another minute or so. But
Sure.
Have you had a good day so far, Doctor? Oh, my name's Jamie, by the way. Nice to meet you. It's a pleasure having you here.
Thank you, Jamie. Yes, I did. Yeah, it was a busy day. But overall, yeah, it was quite nice. A good end to a Friday with this talk, I think. Um, but yeah, how was your day?
Oh, very well, thank you. Thank you very much. I was looking forward to this all day. I was looking through some of your paper. I'm just an amateur who just really excited with science, so there's a lot I'm kind of going over my head, but I'm very excited to hopefully hear you explain some of it through. So that's very looking forward to this.
Thank you. Thank you very much for the kind words. I think we are all amateurs in science. um, and I also look forward to, yeah, passing on the knowledge that I have gained in the last few years.
Really glad you were open to being here on the platform. There's a lot of speakers that have never done it before and found it to be surprising but also enjoyable, and I hope you can find it the same way.
Absolutely. I think this is a new experience to me. I've never had a podcast form of a science discussion. And yeah, I think this is a great forum, and I congratulate you and your team who started this activity.
okay, well, I guess we can get started now. So, welcome everyone to the Science Society. Today's guest speaker is Dr. Saeed Ghazi Sarwat. Um, Dr. Sarwat is a research staff member at IBM Research in Zurich, Switzerland. His research is primarily in the exploration and use of processing in-memory technologies for deep learning accelerators, both in the electronics and optics domain. His research often combines device design, new functional materials, and algorithmic breakthroughs in creating ideas that have a shot at becoming disruptive technologies. He's a recipient of an Oxford University Felix Scholarship, Innovator Award by the Indian National Academy of Engineering, a Foundation Award by the Society of the Automated Engineering, and a Brahm Prakash Medal. He is an innovator of 11 international patents, and his work has been featured widely over the last several years in reputed journals and conferences. So with that, Dr. Sarwat, you can begin your content to the audience. We have a merged PDF at the top of the room that has both papers that can be discussed today. Dr. Sarwat, the first one is the Nature Nanotechnology paper, and the second is the Nature Communications. Whichever order you'd like to choose, but the audience is able to follow along the two papers. So with that, you're welcome to proceed.
All right, thank you for the very kind introduction, Saina. I think I'll go with the order that you have.
Okay, but first, I'm sorry. First, we have a tradition where we like to ask a very general question, and then you can launch into your content. So, Jamie,
absolutely, go ahead.
Thank you very much, Una. Yeah, that's an incredibly impressive background that you've got there. And one of the things that we always find interesting here is if you could maybe start off by telling us what is it that got you into science in the first place? What fascinated you and what's brought you on this path?
Oh wow, that's a deep question. Right, so I think it's the name and the fame of being a scientist. Okay, that's a joke.
That's fair.
Right, so speaking very honestly, right? So I come from a very modest background, from a middle class family in India, right? And the way we were brought up by our parents was pretty interesting. So we were taught from very early age that the path to improving your life is education, right? There's no other option. You have to educate yourself to become a better version of yourself, right? And I think to me, it was the interest and the vigor to learn new things that eventually led me to doing science. And yeah, so I think the thirst for education was really the driver to becoming to following a path in science for me. But if I really look back now, as a kid, I would say I was a very inquisitive person, and I thought of myself as a person who would love to inform people about things they didn't know, and be essentially a biological Google, right? In my friend circle. So the thirst for science started there, right? So I wanted to know more about everything so I can let people around me know more, educate themselves. And this is the first priority for becoming a scientist in my mind, right? You have to have that motivation and that figure to take a path in science. But the turning point really came in high school. So I remember being a part of a team, a quiz team, and we were trained by scientists who pursued material science. And in our training, they gave us models of atoms. They showed us how atoms move in materials, right? So and that was something that struck me, right? So I was just amazed by knowing the fact that we had reached a point that we can see atoms move, and it was that particular experience that just changed my perspective of what I wanted to do in the future, right? And this is how I became a scientist. Yeah.
So was this your apple dropping on your head moment, as the legends go?
Not really, because that was it was not apple dropping on the head, but rather how would I say, watching an interstellar movie, right? So seeing something that you have never seen before, right? So as a kid, all you cared about was knowing. So there were two things I could do as a kid, right? I can watch a lot of cartoons and anime and gain knowledge on them, right? And this is what I did for the longest time until this incident happened. Going from learning about cartoons and animes, you're shown a picture of a micrograph where you can see atoms, and that was a game changer, right? Yeah.
That's incredible. That's even quite inspiring. And one last question before we get into it then. And so what is it, was it this then, this knowledge that brought you to the field that you're currently studying? Did you just pursue this directly all the way to here?
Oh, no, no, absolutely not. So I started my research career quite early on. In fact, in my second year, in my sophomore year of my college, and I started off with traditional material science research, which is metallurgy, right? So study of metals. That is what I started with. Um, but 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 I slowly evolved in my approach to science. Right, I think that as a scientist, I'm not bound to a certain field, but rather bound to multiple disciplines. Right, and this field that I'm pursuing now, it just happened, uh, and I embraced it as it happened. Yeah.
That's incredible. It's fascinating to see that so many scientists end up in remarkable places from from such unexpected directions.
Oh,
Um,
absolutely, absolutely. Yeah.
yeah,
I think that the key is to be just open to solving important problems, and if you can do that, then I think you can fit into any field, even the fields you never imagined you would be doing, right? So on a side note, in college, I intentionally did not take the field of electrical engineering or computer science. I was scared of coding, right? The C++ blue screen that would appear on the desktop would put me off, right? But today, all I do is coding. All I do is electrical engineering, right? so I come, so yeah, turning point.
that's incredible. Thank you very much for that. Okay, Serena?
So yeah, wonderful. Okay, so take us away.
Sure. So, to set the stage, I would start off by saying that we live in very interesting times, times when we are fundamentally rethinking about how computers should work. Right? We have not done this before. We had a design of a computer back in 1950s, and we have not changed it. Right? And today we live in an age where we want to change the way computers should work. And the reason for this is because we cannot process the data that we're generating these days with the computational power that we have, right? And the data that is being generated today is not just the data by you and me on Snapchat or on WhatsApp, right? It's also by the machines that we have built. So in fact, machines today are generating more data than humans, right? And this is an exponential trend, so it's bound to increase. And one option to creating new computers is growing brain inspired, or otherwise called neuromorphic computing. So neuromorphic computing, in the broadest of definitions, is a subset of neuromorphic engineering, right? And the goal of neuromorphic engineering is to understand the brain, the computational models of the brain, by emulating them on hardware, right, on silicon. So that's the goal of neuromorphic engineering. What we are trying to do, what my team is trying to do, is we want to take this emulation further, right? We want to make this emulation for useful, for computations, useful for operations that we need in our daily lives. So neuromorphic computing is a field where we're using the ideas of neuromorphic engineering to do useful computations. And like being said, a neuromorphic computer takes inspiration from the brain. We do not understand the brain in its fullness of glory, right? And it will take us some time before we even reach that point. But right now, what we're trying to do in the field is replicate the building blocks of the brain, which are the neurons or the nerve cells, right? Specifically, we're trying to emulate the components such as the neuronal soma, the neuron, or the synapses that connect the neurons, and the dendrites, right? These are the three building blocks that we know of as of now, of which do computation in our brain. And this is the approach that we're taking in this day and age. However, so far, what we've achieved, and quite remarkably what we've achieved, is building a model where we take the traditional approach of artificial intelligence or learning, right? So modern hardware, it has a bunch of synapses and neurons, right? We train the synapses to a certain task, and once we train the synapses, they don't change, right? This is based on the idea that the neurons that fire together wire together, right? The famous Hebbian learning formulation by psychologist Daniel Hebbian. However, modern neuroscience has taught us that there's more action happening than just wiring together, right? So neurons, when they fire together, they not only wire together, but they also have a range of temporal changes at the synaptic junction, right? It's not a simple step function. It's a temporal change in the synapse, and this is one area. This is one area which our hardware has not yet captured in the fullest of sense, right? The temporal dynamics of synapses, the temporal dynamics of neurons. This is something that is still being investigated. So the first paper that you see on the PDF is related to building a hardware, a synapse, an artificial synapse for the neurons to connect with, that cannot only learn the way traditional neuromorphic hardware does, but it also has this temporal dynamics ingrained in it, right? And the example that we show in this paper is of a memory technology called phase change memory. Now, phase change memory, you must already be familiar with phase change memory. This is the same the technology that goes on to the DVDs and CDs, right? Some of you may be too young to know what DVDs and CDs are, but the way the DVDs and CDs work is using something called a phase change material. And in the phase change material, the idea is you can toggle the way atoms are arranged. And by toggling how the atoms are arranged, you can change the property of the material. You can change its optical properties as well as electrical properties, right? So what we did in this paper, the one that you have on the screen, is we used a phase change material based device where so the phase change material device is a synapse. We use the idea of the atomic positional changes for storing the strength of the synapse, right? That's how strongly the neurons connect is by the strength of the synapse, the synaptic efficacy. But what we did on top of that is we introduced the temporal feature by using another property of phase change material, which is its semiconductivity. So semiconductors are ubiquitous, right? Our mobile phones and computers, they run on silicon. Silicon is semiconductor, and so are most phase change materials. So what we do with the new control is we change the electrical conductance of the phase change memory device, also by using its semiconducting property. And this semiconducting property is transient. It only exists as long as there is an external signal applied to the device, just like transistors. So now you have a device where the atomic positions of the atoms dictate what is the long-term plasticity, right? The long-term memory, so as to say. And on top of that, there is a control knob that further controls the synaptic efficacy, but temporarily, as long as you want it to be there, right? So this is what we do. So in the first paper, we try to capture the synaptic plasticity in a more rigorous way, and we do that by having this additional knob on the device, right? And what we show is, hey, this is not just biologically inspired feature of a synapse, but this has impactful and useful implications, right, in machine learning. So the first demonstration that we have is of a new form of learning. We call it short-term spike-independent plasticity. And the idea here is that you can recognize it. So the example that we show is of visual perception. So if you can scroll down on figure, where is it? Right. So if you scroll down to figure 2, you would see that there's a person, there's a computer vision who is trying to see a boy and a girl, right? So in traditional artificial intelligence or machine learning approaches, you must train the computer vision with all possible postures of the boy and the girl, right? That is a training data set. You have to train with all possible transformations. Now, when you try to run your machine learning model in real life for inference, that we say, then the machine learning model would do very well on the data set that it has seen, right? The postures of the boy and girl that it has seen. But it would not do so well on the postures of the boy and girl which it has not seen, right? And this is very different from how we learn things, right? As humans, you can show me, the picture of Jamie. It's just put to Jamie, and no matter what Jamie does, no matter how he moves, I would be still able to tell that, hey, that person is Jamie, right? So this apparently could come from this temporal dynamics of the synapses. This ability of the human brain can come from the temporal dynamics of the synapses, and this is precisely what we emulate. So what we do on the hardware is we train the network with some images, and then we show the images that the network has never seen before, right? And the network can still recognize the objects. Right? This is the holy grail in a way. And it's a holy grail because you're firstly, you do not have endless supply of training data set, right? You don't have all possible postures of the boy and girl. It's impossible, right? And second, if you want your model to become better, you need more training data set, which means you have to spend more energy and time to train the model. What we are doing is we're training on a subsample data, but doing inference, it is still learning, right? It can still recognize things. So that's the first application that we demonstrate, right, of what such a device can newly do, right? So that has to do with the synaptic plasticity at the scale of individual synapses, that is local to individual synapses. The second application that you see, that you would see on figure 5, I think, of the manuscript, is what we call homeostatic plasticity, right? So the synapses have multiple plasticity models, right? There's the local plasticity rules, and there are also global plasticity rules. So what we show in figure 5 is that, hey, you can do more interesting machine learning tasks by using the global plasticity feature as well. So what we solve in that example is a very difficult problem to solve, which is a combinatorial optimization problem. This is what we call a non-polynomial problem. It's very hard to solve with traditional computers because you never know what the solution is with such problems, right? Just to put in context, this is the same problem that is being solved in protein folding, or the same problem that's being solved in scheduling how the airplanes should fly, right? So they don't crash with each other, right? The routes they should take. It's a very difficult problem. So what we do here is we take a biologically inspired approach where we have our neural network and we inject noise to all the synapses, right? And we inject this noise to all the synapses via the semi-conductivity feature of the phase change memory. And by injecting noise, we are able to solve this hard problem quite efficiently and in a very energy efficient manner. Right. So these are some toy examples, so as to say, to illustrate that what a neuromorphic hardware can do if we can emulate the biological counterparts better, right? So yeah. So if there are questions on this part, I'll be happy to take.
Hey, yeah, thanks for joining us today. This is super interesting. I'm just glancing through the paper here. There were a couple of questions I had. In terms of, yeah, I know you mentioned just now energy efficiency, which is super important aspect of motivating these kinds of new architectures. I'm curious how it compares to other like standard machine learning metrics in terms of training and performance. And if you could unpack a little bit how the training works, I would appreciate it.
Oh, right. So at least we have to give you concrete figures, one has to do benchmarking. So at least in this paper, we have not done benchmarking, where we have compared this architecture against other. But in a different paper, which is not linked here, we have shown that this approach is not only energy efficient, it is also more accurate than conventional artificial neural networks in terms of its accuracy, right? Um, Sorry, what was the second question? I'm just trying to recollect. What was the second question that you had?
Oh, it was just about the details of how the training procedure
Oh,
works.
right. So, like I said, traditionally, if one has to train artificial neural networks, the network must see a lot of training data sets, right? And this is where the bulk of energy consumption lies, right? Just to give an example, there are models in artificial neural networks that take the same amount of energy as powering the entire New York City, right? So they're super energy intensive, and that energy expense comes from the fact that you have to train them with a lot of training data set, and you have to train them in a manner which is not biologically inspired, right? Um, Although we have not done benchmarking with our approach, what we show is that one can take a biologically inspired approach where there's no need to learn on a lot of training data, right? You can learn on a very few training data sets. That's one point. Point two is you also operate in a manner that's biologically inspired, meaning you operate with spike trains. You work with action potentials, right? And this gives a lot of energy gains to the algorithm or to the hardware. So that's where the benefits really lie.
So that's
Yeah.
awesome. That's what I like to hear about this. This is what I'm hoping. I feel like the current state of AI and where we're heading and the trajectories of all that it's just kind of awkward. I had a couple of questions about in Figure 1. You're kind of outlining some of the that you have these synapses that have different states, different temporal features, and this kind of having a variety of temporal features for synapses has already been shown to be very advantageous in simulated neural networks as well. So this is really cool. I was curious about whether there's I see long-term potentiation, short-term potentiation. I'm wondering if there's any mechanisms for depression at this point.
Oh, right. Oh, there are mechanisms for depression. So I think in the supplementary information of the paper, you would see synaptic fatigue being illustrated. So in the main test of the paper, we focus on facilitation. This is the synaptic facilitation process where there's an increase in the synaptic efficacy, and you need this for the task that we solve, right? But the but the cool thing is, like you said, you can also emulate synaptic fatigue, and not just synaptic fatigue. You can also implement other bunch of temporal dynamics. You can also put in noise to the system, right? So our neurons, they sit in a medium that is basically a fluid, right? And ions move around, they diffuse around. So the medium is not the constant. There's a lot of noise happening, right? You can also add that on top. So this feature, this idea of temporal dynamics is invariant to the operation, right? You can do a bunch of things with it. Yeah.
Also, I don't mean to hog the mic, so please, and just stop me. I am curious though if the synapses always work completely independently of each other, or if they are able to compete in some way. I'm thinking about some of the more nuanced plasticity mechanisms we see in the brain at the level of, you know, dendritic branches and things, where they're ultimately the competition arises from you know, leaking signaling between synapses and competition for resources from the branches. I'm curious if there's any coupling between the synapses in this architecture.
I see. I see. I'm not very familiar with the specifics of the plasticity model that you're referring to, but definitely, right? So with the idea of synaptic fatigue, you can put in this leaky term there, right? You can decrease the connection of your device or the synapse via fatiguing it. So that is very much possible on the hardware. Yeah, yeah. So at the level of individual synapses, you can have this leaky term involved. Yeah. Traditionally, leaky term is involved at my understanding is, so the leaky term comes at the neuronal soma, right, at the neuron, not at the synapse. But in a way, you can see the leak as the synaptic fatigue, the fatiguing of the synapse. Yeah. So it is doable. Just to set an example for this, right? So it is understood to an extent in the brain that synaptic facilitation happens much in the central of the cerebellum, right? But synaptic fatigue is equally important, right? This is the mechanism that allows us to go to a disco party and still pinpoint to where your friend is, right? This is a sound localization task, right? So if you're in an environment where there's a lot of sound and you still have a friend shouting your name somewhere, right? You will be still able to locate that person. And this is where the idea of synaptic fatigue comes in. Yeah, so all this can be implemented and is to be seen what we can do with the hardware. Yeah.
So I have one last kind of broader question, and then I will
Sure.
get out of your way for everyone wants to hear your presentation.
No worries.
So my question is about we're talking here about, the claim is that the architecture is you know, non-von Neumann. I'm
Right.
curious in what sense that architecture is being broken. So, like, for example, you typically think of a processing unit, so you'd have, like, you know, a logic unit,
Right.
processor registers, a control unit, so you'd need instruction, program counter, memory. I think the traditional definition also includes, you know, external mass storage and I/O. So and like, I think that, you know, the term has evolved to mean stored program computer that requires instruction fetch. So it has this architecture broken the need for stored programs in that sense, or
Okay, so the way you can imagine non-Feynman computing is, imagine your USB drive becoming intelligent, right? So right now your USB drive, all it can do is it can store data, right? And to be able to do something useful with the data, you need to connect the USB drive to the computer. But in non-Feynman scheme, you can perform computations without ever moving the data. So you can have the data stationary at place where it is, and then you can do operations on the data. So these are the instructions that you're talking about. So you can, for example, if you want to do a multiply operation, you can do a multiply operations without ever moving the data from its location. So this is where the idea of in-memory computing or non-Feynman computing comes in. All that said, there's still so non-Feynman computing. So non-Feynman computing is not completely, without the conventional methods. A part of a computational operation is done in a non-Feynman scheme. Some operations must still be done in the von Neumann scheme, right? So this has to be understood. To put an example, most artificial intelligence algorithms, right? 70 to 90% of the mathematical operation they need is a matrix vector multiplication operation. That constitutes around 70% of the operation that needs to be done. And this you can do in memory, non-von Neumann way of operation. But there is this 30% of other operations that must be done. Those are still done, in a von Neumann scheme of some sorts. I hope that answers the question. Yeah.
Yes, thank you so much.
You're welcome.
If I could just quickly ask a question, please, Doctor. When I was looking at your paper, when you're talking about the low volatility, I'm guessing that's at the short term, the long term memory, right? That doesn't change as much, of the plasticity as you say, volatile, and the short term is more volatile, right? That's how you have it. Yeah. And my question is, in the paper you mentioned short-term plasticity can be used as a filter. Could you explain what exactly that means and what that is, please?
I'm sorry, I didn't really hear well the last word. Short-term plasticity can be used
as a filter.
As a filter. Okay.
Yeah.
Right. So this is right. Absolutely. So like we discussed a few seconds ago, there are different models, there are different synaptic models, plasticity models, right? And each model does something different. So the long-term plasticity means that it provides memory, right? This is how we remember things. Short-term plasticity has to do with the temporal feature, where the memory is lost after a certain time duration, right? And traditionally, this is how we came to know of short-term plasticity in neuroscience, right? If you were to inject a train of pulses to a certain synapse, right, with different frequencies, right? So imagine you have 10 input pulses to a synapse, a biological synapse, and you're modulating the frequency between, or the time period between individual pulses. You will find that the output depends on the frequency that you have. So this is where the idea of filtering comes in, and this has to do with the STP, short-term plasticity. Essentially, what happens is, if you increase the frequency of your input, the output of the neuron or the postsynaptic spike would not happen. It would either be of very low amplitude, or it will not happen if the frequency is high. So this is where the idea of filtering comes in. The neuron is now the output of a neuron not only depends on the number of input spike trains, but also the frequency at which they arrive. And this is a filter essentially, right? You're filtering out information based on their temporal dynamics or the temporal state. Right. So just to give you a biological sense of where this comes from, right? So the long-term plasticity of the synapses has been the different ways to reasoning how it happens. So the long-term plasticity of the synapses has to do with the ion channels, the number of receptors, right? If you have more receptors or specific receptors like MDA, then you have long-term plasticity. Short-term plasticity, however, comes from how much neurotransmitters can you release to the synaptic junction, right? And if your input frequencies arrive at very high frequency, then you are depleting the amount of neurotransmitters in your synapse, right? So before the synapse can replenish its concentration of amount of neurotransmitters, the next spike comes in, right? And because there are no neurotransmitters to pass on the information to the next neuron, the output of the postsynaptic signal will be small, right? Yeah. So this is the filtering approach. Does that answer your question?
Yeah. Thank you. I mean, yeah, it brings up lots of more questions, but thank you very much. Yeah, that's fascinating. Thank you.
Right. You're welcome.
Yeah, do you want to continue with the presentation? Thank you.
I cannot hear you well.
Do you want? Yeah, so we can continue with the presentation, and we can
perfect.
hold questions till a little later.
Oh, sounds good. Sounds good. Right. So I think now, all that said, let's now talk about the second paper that we recently published. This should be on the second document of your PDF, right? And this again is a continuation of what we just discussed, right? So we discussed that the synapses are rich. They're more functional than we think they are, right? And they're more functional because of the plasticity mechanisms they have. Um, so all that said, in this paper we came up with a new device concept that allows us to do even more cool things, right? So what we did in this paper is we created a nanoscale device, which we call an optomemristor, that can integrate not just electrical signal but also optical signal, right? The analogy that I like to draw is from the field of optogenetics, right? So optogenetics has been a game changer in neuroscience. In optogenetics, what one does is they modulate the neural activity in the brain by shining light on the neurons, right, or the modified neurons. And this is essentially the approach that we take in this paper. We create an artificial emulation where the synaptic activity can be modulated with an external signal, the third signal, which is light, right? So right, so this is the core of this paper. It again is in the line of making neuromorphic computing hardware more biological-like, right? It's in the same line of thought. So if you now go to figure 3 of this paper, you would see what we try to do with the device. So given that we can now modulate the synaptic efficacy, not just using the electrical signals on the hardware, but also optical signals, we went on to implement an algorithm of reinforcement learning, right? To set the tone for it, if you play the game of ping pong, right? If you play table tennis, to learn to play table tennis, you serve the ball on the other side of the table, and then you wait for the result, right? You do an action, and then you wait for some time to know if the action was successful in a certain task, right? So if the ball lands on the table, it's a happy thing, right? It's a reward. You basically get that reward, and you tell yourself, "Hey, this is how I need to serve, and this is how you learn how to play table tennis," right? And this set of actions, they happen, in seconds, in minutes, or even days, right? It's reinforcement learning happens in a longer duration of time. This is very different to what we think of as learning in the brain right now. When we think about learning, like I said, neurons that fire together, wire together, but the firing happens in the time scale of milliseconds, a thousand of a second. That is the time scale that the neurons are working with. But surprisingly, the tasks that we learn every day, they happen in seconds or in hours, right? Not in milliseconds, right? And they happen with some reinforcement. Reinforcement can be bad or it can be good, right? So this is what we went on to implement here. So what you see on figure B is a toy demonstration where we made a mouse, a rodent, learn to navigate. Right? We made the rodent learn the path to find cheese in a maze. Right? And this is a reinforcement learning idea. So what really happens in this particular demonstration is that the rodent, it is moving randomly in the maze, right? And when it moves randomly, certain cells in the brain fire, right? And those cells fire specifically depending on where the rodent is, right? But the rodent is also expecting a reward, right? So when the rodent moves, it is also expecting a reward. It wants to find cheese, right? So the rodent moves, something as it moves to a random location. It is expecting a reward, but the reward is not received, right? So it comes back to its original position. It tries some other route. It doesn't find the cheese. It comes back. But then in one possible scenario, it goes to the location of a cheese, expecting it will find a cheese. And if it finds the cheese, then it automatically learns the path to the cheese. It remembers the path now. You can put the rodent anywhere, and it will now find the path to cheese. And this is the idea of reinforcement learning. Specifically, what we do is we use light as the reward signal. So when the mouse moves, it is expecting light as a reward signal on the synapses. And when it finds the cheese, the light superimposes with the electrical signal, and the synaptic efficacy is changed in long term. Long-term plasticity happens. So this is the specific demonstration of reinforcement learning using what is called three-factor plasticity, right? So traditionally, when you talk about plasticity, it is two-factor: presynaptic pulse, postsynaptic pulse. In reinforcement learning, it's three-factor. You also need to have a reward signal. And this is how things happen in the brain, right? So this is where the idea of dopamine comes in, or serotonin comes in, right? The neuromodulators or neurotransmitters. When we perform a task, we expect a reward. If we get a reward, dopamine is released in the brain, everywhere in the brain, and only in the locations where activity happened, those synapses become stronger, right? And we can do this now in memory in a non-von Neumann way of computing. So here we implement reinforcement learning using this idea of three-factor plasticity. And this is yet another example that goes on to say that, hey, you can really do cool things if you emulate the brain better, right? And this is precisely what we are doing here. Yes, we are trying to emulate the brain using its mechanism that it uses. All right, so this is another application, and this is where the idea of temporal signal again comes in, right? So the reward signal is temporal. It happens for a certain time and then it disappears. So this temporal idea is again featured in this application, and we implement that, right, with this device. All right, so now let's move to the second application that we demonstrate. The second problem that we show is the idea of shunt inhibition, another popular mechanism in the dendrites of the neuron, right? Now, to set a stage for this, AI or the mathematical models for AI, they emerged in 1940s, right? By 1950s, we in a way knew what mathematical models we need to use, right, to make a machine that is biologically inspired, right? But then from 1950s to 1980s, this is what we call the AI winter. That can happen in AI, right? And one reason why there was an AI winter was because of a problem called XOR. So XOR is a logical problem. It's like AND gate or OR gate, right? It's a logical problem which is non-linear, and its non-linearity implies that it's very difficult to solve using linear operations, which modern machine learning does. So modern machine learning is all based on linear operations. So what we show in this particular demonstration is that you can use our devices as input to dendrites, right? And with that, you can achieve a single neuron solution to this very difficult problem of XOR. And the highlight is a single neuron
Excuse me.
solution.
Excuse me.
Sure.
There's a slight disconnect. I just want to confirm. What are you saying that the modern deep learning algorithms are linear? And
Oh,
what
right,
you're saying.
right.
So
Yeah.
are you saying something like back propagation is linear?
No.
What are you saying there?
No, I'm saying that the linearity is this idea of matrix vector multiplication. So when the presynaptic spikes come to the neurons, right? So the operation of the operation that takes place between the input and the synapses is linear. So that's the linearity. There's no non-linearity in the synapses. The synapses are linear. They are like weighing elements. Yeah. So that is the linearity part of the modern neural network. But yes, there's non-linearity that happens at the neuron in modern artificial intelligence and in backpropagation. But that is different. Yeah.
So biological neurons, if you say they take inputs and they produce an output. So
Right.
there's an input and output. So is this linear or non-linear in definition? What is this? Or of course, if
Right.
it is below certain threshold.
Oh, absolutely. So just to break down the process, you have input that comes to the dendrites, right? Then they go into the synapse, and they come, and then out they come to the neuron body, right? So before, uh, so the output of the synapse is a linear operation. The output of the neuron is a non-linear operation. Does that clarify? So the synapses per se are linear.
Okay, sure. We'll chat later. You can continue.
Are your dendrites linear here?
Sorry, I didn't hear that.
Are your dendrites linear in the hardware?
Yes, so right, yeah, so right. So devices that we have, they work with this linearity. That's correct. Yes, yeah. But again, dendrites make connections using synapses, right? And synapses are linear in the traditional form, right? The long-term plasticity form, not in the short-term plasticity. The long-term plasticity form of dendrite synapses is linear. Yeah.
Yeah, I studied dendrites biologically, and I'm always thinking about the added compute power from the well-known varieties of different types of nonlinearities in the dendrites themselves.
Oh, absolutely, absolutely, yes. So this is where this idea emerged, right? So in fact, recently it was shown that one can solve this problem of XOR using dendrites, and the feature of dendrites that is used is its nonlinearity, precisely the nonlinearity of the dendrites. Yeah. So again, one has to distinguish the different components, right? Synapses, neuronal body, and the dendrites. Yeah. Um, okay. Um, I hope that was clear. Anyway, so what one can do is one can solve the problem of XOR nonetheless in modern artificial neural networks using multiple neurons, right? You can always have a network of neurons and solve XOR. So you map the nonlinear problem into a linear domain with multiple neurons, and you solve XOR. This is doable, and that is how we came out of the AI winter, right? Uh, but we have recently understood that dendritic computations allow you to make a single neuron perform XOR. And this is the approach that we took here, right? In a different flavor though. So we use this idea of shunting inhibition of the synapses, of the dendrites, right? And the idea of shunting inhibition is that your input signal that flows to the dendrite can be shunted away before it goes to the neuron, right? And this is precisely what we did with our devices. We use the electrical signal and the optical signal to do this operation, the shunting inhibition operation, and via that we are able to solve this XOR within the same using the same device. Yeah, so that's one another example of how this new type of devices can help us emulate some of the biological features in a more robust way, right? Now that said, this is still all proof of principle, right? You're not seeing a network of devices here. You're just seeing the notion that if one can emulate the neuromorphic principles better, then the computation problems we are trying to solve now becomes easier and more efficient. Right, good. Yeah, I think that brings me to the end of this article as well, and I'm happy to take more questions.
So I have
Um,
few, and you can choose not to answer as well. I basically attended this debate on neuromorphic computing versus traditional computing with
Sure.
Lanya Kuhn, who's like the father of modern deep learning. He showed some skepticism. He basically asked some questions to the NVIDIA chief who's leading this
Oh,
initiative.
absolutely, yeah.
Right. The fundamental problem is that what so the way the deep learning algorithm came about and how Google has designed the specific chips to do the tensor calculation is as follows. They build an algorithm first on paper. They mathematically solve it on paper, right? There was no computing without computer. Then they got something called computer, and they started training those algorithms slowly. Then they realized, okay, let's design. It would be better if we design chips which can optimize these algorithms specific to
Absolutely.
right. And but what we see in what you see with chips like Lohi, you call it Lohi, right? This
Yeah.
Intel chip, right? So Intel came up with this chip, right? But apparently, these why design a chip for algorithm which doesn't work, right? Yeah, there are no algorithm which we have seen as per se. What we have seen is that we have taken reinforcement that the already tested functioning deep learning algorithms, and now we are basically taking them and testing it on chips like Lohi. So, so the thinking is, and the execution has been really opposite in a way in which a traditional neural network came about, and how we are approaching, let's say, and we are all for success for this neuromorphic computing, right? It would be great if we can pull this off. But there's. I just want to make a philosophical point as well. It might sound very
Mm-hmm.
philosophical, but let's see. When well, the guy who
Armish,
invented.
Armish, are we bringing this to a question?
Yes, I think I already asked two questions in between. I so this is Gandhi,
Oh, I
I
didn't
hope
see any
you have
other
noted.
questions. Yeah.
Right. So the hope you have noted those questions. So what
No,
algorithm
I
we have?
haven't. I haven't seen your questions. Sorry. What are your questions?
Right. So the question is, what are the algorithms you which are new, which are different than deep learning, which neuromorphic computer has come up with, which can solve the problems which we are, which
Oh,
deep learning cannot now. What are the
absolutely.
algorithms, not the chip design? So I have, I
No,
do
no.
not.
This is a very fair and good question, right? So there's a reason why you don't have neuromorphic chips that are mainstream. There's a reason why artificial intelligence with these deep learning models, perceptron models, are in the market and not the neuromorphic chips, right? And the reason is we still haven't figured out a way to make this neuromorphic chips or algorithms more accurate than what we have with artificial neural networks, right? So that's the bottom line. So what we want at the end of the day, as a consumer, right? We want our computers to consume less energy and be extremely accurate, right? What we do not care a lot is what is happening in the background. It could be running a Sparky neural network, neuromorphic computing, or it could be running an ANN. So it's a very fair question, and this is where the research of Sparky neural network lies in. What are the algorithms where a neuromorphic chip would excel artificial neural networks? And everyone is doing this. So for example, the first popular chip was IBM Blue North in 2013, and then came Lohi, right? And what Lohi is doing is it has made its chip open source. So as a neuroscientist, as a computational neuroscientist, you can run your algorithms on their chip. And they have made it open source simply because they want to find a killer application for neuromorphic computing. So yeah, so that is where the debate is. What we are trying to what we are trying to do now is basically say that you can make some of the tasks more efficient using these ideas of neuromorphic mechanisms. Because the other way of deep learning is very expensive. But I do not say, see, artificial neural networks are amazing, right? They're one of the best discoveries that we have had in many years, right? And they're not going away. But neuromorphic computing may allow us to make our computers more efficient. So, and this is really needed. So maybe do not maybe in some applications you do not need accuracy. You just want to save power. For example, you can have your CCTV cameras, thousands of them on the street, and if you use a neuromorphic sensor, a chip, then you will save thousands or 10,000 x folds of power, because power is important there. So it all comes down to application, really. Yeah. I hope that answers, yeah, your question.
So I had a question along this line. In terms of in your first paper, you
Yeah, sure.
mentioned there was a result of it requiring fewer training examples and learning faster.
Oh,
Could
right. I
you
can.
could you get into a little bit more of the mechanisms of that? Because that's certainly a contemporary weakness in deep learning.
Yeah, absolutely, absolutely. So this is one algorithm. So again, I was coming to this point, right? So in the first paper, we talk about one potential algorithm, right? We test this hypothesis on the chip. We came up with an algorithm where we do not have to train the neural network in the way you train an artificial neural network. We don't train it with all possible images in the task of visual perception. We only train it with a subset of images. And when the model has to perform the task of, I don't know, classifying things, it can still run, it can still learn as it is doing, right? So this is what we do. So there's this idea of short-term spike time independent plasticity. It's an algorithm that we came up with that allow you to do inference, this visual perception in a more robust way and also more accurate way. There's another paper that's not shown in your PDF, but there we have compared this idea, this algorithm against conventional neural networks. We compared against CNN, LSTM, RNN, and we show that with proof that, hey, with such algorithm, you can not only have the highest accuracy for this task, but also you can be more energy efficient. Yeah. And this purely comes from the fact that we are including the short-term dynamics in the synapses. Yeah.
So you also mentioned that spike trains in particular gave an advantage over conventional neural networks.
Absolutely. Yeah.
Could you go into a little more detail there?
Right. Sure. Absolutely. So a conventional computer, it runs on what is called a clock, right? You have this clock signals going on in a computer, and all the input, all the data that's in your computer, it moves all the time because of this clock signal, right? In the brain, it's not like that. There's no synchronization in the brain. You have spike trains that are asynchronous, meaning they spike at random times, right? And if they spike at random times, it means you're only computing, you're only consuming energy when there's a spike. When there's no spike, your brain is ideal, right? It's not consuming any energy. And this is why our brain is so efficient. Our brain runs at 20 watts, right? 20 watts is the energy consumed by the light bulb on your roof. And that comes purely from the fact that the brain is not active all the time. It only becomes active when there are spike trains, and the spike trains happen only when you're doing a task, right? And this has actually been implemented on hardware. There are commercial neuromorphic sensors that you can employ to see the change of scene. So, for example, imagine a camera, a neuromorphic camera that works on the spike trains. The camera does not consume any energy when nothing in its view change, right? There's no spike trains. But if a person appears in front of the camera, something has changed in the view of the camera, and this is when spike trains are generated. This is when computation happens in the camera, and this is the idea of low energy, low power consumption in the brain because of the spike trains.
If I may add, actually, generating an actual potential almost costs nothing. It's more the work around it to clean up the brain and repurpose neurotransmitters, what the glia do that consumes more energy. An actual potential itself doesn't consume
right. But my point was computation happens when there are action potentials. Yeah. Right? There's no computation when there are no action potentials.
So what I think is really exciting is that you have the inhibitory signal also there in your second paper, because this should give a way more granular information processing that is more efficient and also more detailed. Did you see that? Do you generate a better, let's say, visual processing basically?
Oh, right.
You edit that?
So this is a work in progress, right? So there are this machine learning algorithms which use this idea of competitive learning, right? You learn by competing with other neurons, and this is where the idea of inhibition comes in, and this is something that we're looking into right now. So we want to build this models of winner-take-all neurons, where the property of inhibition is exploited. That's a very good point. Yeah, but this is exactly what I'm trying to say, right? Because your devices can do all this cool stuff, you can implement the nice features of the brain, and allow some of the computational ideas in neuroscience to be implemented, and from that new algorithms can evolve for machine learning, right? So
Do you also generate upstates? We had a guest speaker here from Max Planck Institute. He taught also about neuromorphic devices that basically generate an upstate, so basically a more excitable state after like a timely correlated inputs would come in. Do you also have?
yeah, absolutely. This is where the idea of this reinforcement learning comes in. So on the second paper, I think figure 3, right? So there's an up state that is created, and that up state, that up state becomes a permanent state only when there's a second signal, the reward signal, right? So it is expecting some input, and if the input is correlated, then it becomes stronger. The synapse become more stronger in their strength. That's right.
So how does the system then select if information? So it doesn't actively select, right? If an information is important, or if it's noise, is there, the brain kind of does it a lot with combining it with emotions. If something happened that is combined, let's say with the emotion of fear, which happens like in the amygdala, or something good,
Sure.
like the fast processing would be the amygdala of the labeling. Do you have that implemented, or is it for now?
No, but again, exactly. But this is again the idea of, so the brain, because it functions on spike trains, it uses this idea of temporal correlations, right? So temporal correlations are at the heart of neuromorphic computing. You try to correlate different inputs. If the different inputs happen at the same time, then you learn things, you execute computations. Otherwise, you don't, right? So in this framework of Hebbian learning or long-term plasticity, it is a correlation between the postsynaptic spike and the presynaptic spike. That's how you learn. That's how you memorize. In this framework of reinforcement learning, this is the correlation between your presynaptic spike and your reward signal, right? And this is the reward signal that you're talking about right now. This emotions and the serotonin and dopamine, right? So they are the reward signals. They must be correlated with a certain part of spike activity in a brain. If they are correlated, then the synapses corresponding to that region would become stronger. So that's the correlation. Yeah. Does that answer your question?
Yeah. So will you have the possibility of basically generating networks that have then different levels of hierarchy? That you will have different levels of neural networks like this with different hierarchy levels. Are you planning on building something like it? So basically building a whole brain based on this.
I think that's a holy grail, right? Building. First, one has to understand how the brain functions, and I think this is a very difficult task, right? And the task simply is difficult because we cannot replicate how the neurons in the brains are connected, right? The neurons in the brain, they have the three-dimensional connectivity, right? What we try to build on chip is 2D at most, or 3D that we have right now. But building hierarchical models are difficult. What we can do is we can build 2D models and connect them together to do exactly what you're trying to say right now, right? So one can imagine, this is actually being done right now. So you can have a neuromorphic vision sensor for the camera that I discussed a while back. So you have the component that is sensing the light, right? That's one hierarchy, the retina, the bipolar cells, the ganglion cells. So that's that region, that component. And then you have the back end that is doing the classification task. That's your, the computational part. So yeah. So,
Gazi, I think the question is
Armish,
how.
I believe Wisdom was next. Wisdom?
Yeah, my question is related.
Hi. Yeah, you were mentioning earlier talking about the cameras. I've been reading about these DVS cameras.
Right, dynamic vision sensor. That's right. Yeah.
Excellent. Yeah. So just so I'm clear, is your hardware implemented in this way where there is no clock cycles at all? I mean, I think this asynchronous computing thing is the big gain for energy.
Absolutely. Absolutely, yeah. So the hardware that we have, it can do both. It can work with asynchronous spikes, and it can also work with traditional clock-based signals. So it's invariant to that. The reason I mentioned neuromorphic vision sensor, the DVS that you mentioned now, is to highlight that neuromorphic chips are already out there doing some cool stuff. Yeah.
I'm curious, could you take input from a DVS device?
Yeah, absolutely, absolutely. So you can have this is what happens right now. So you have input that comes to the camera. So camera basically. So the way the camera works is in its traditional form, right? You have a bunch of photodiode or photosensors. They receive an input. They generate spike trains, and then this spike train goes onto your neural network. Yeah, and then the computation happens in the neural network.
Yeah, that's fascinating. The last question I had, I was just thinking about, once you had kind of a large hardware network of these synapses all built up, and you start trying to learn something with it. Are there homeostatic mechanisms? I'm wondering about what prevents the hardware from, going into unstable regimes or
Oh,
getting locked
absolutely.
in with.
Yeah, so I think I mentioned this, right? So in the first paper that you have, right? So we implement homeostatic mechanisms. So and we implement homeostatic mechanism to do some useful computation. In the last figure, we use this noise that happens on all the synapses in the network because of homeostatic mechanisms to solve a difficult mathematical problem. Now coming to the question of adaptation, right? You can find a result in the support information. You can adapt the fine activity of the neuron based on its input frequency. So that can very well be done. Yeah.
Thank you.
So I had a question in terms of, I mean, this is exciting technology. Very next, I hope. In terms of the development, and I understand you're in research, is there been discussions of IBM making some of this available, like say first through the internet, software development kits? And when can we get our hands on this?
I think what we show here, right? These two papers, they're proof of concepts, right? Here we are building just a synapse or a neuron, right? And this is like nothing when it comes to building an AI chip. There's a lot that needs to be done to make an AI chip. It's not just the synapses and neurons, but also the peripheral circuitries, the layout, and whatnot. So at least we do not see this coming out anytime soon. In the realm where you can fork with it. Nonetheless, we have IBM non-von Neumann way of doing things. IBM chips that you can play with. They are available for public to fork with. So these are again the same idea. So in the first paper I said that we were using a phase change memory device, right? We have a chip that runs in the cloud right now that you can play with that is based on phase change memory devices. In that chip, we are not using this property of temporal dynamics. We are only using the long-term plasticity. So you can play with those kind of chips right now. Yeah.
Yeah, I mean, let me push on that a bit. I looked through this experimentals. I know IBM could scale that up if they saw the business case. I used to be there. So I'm just curious if if those business interests start lining up, what are the barriers to scaling that technology? Like if we wanted to,
Mhm.
ramp that up, what have you identified in terms of the difficulties in getting it off the
Oh,
bench?
right, right. So like I said, so IBM already has a chip, right? So IBM TrueNot was the pioneering chip in the field of neuromorphic computing. So there's a full-fledged chip called TrueNot, IBM TrueNot, that is fully based on spike trains and processing models and whatnot, right? Now the challenges that come in front of neuromorphic computing is what I already mentioned, right? So what are the algorithms where neuromorphic computing can do better than what we currently have, right? So that's one, and that has to do with the accuracy, right, of your machine learning task. So that's one of the biggest challenge of spiking neural networks or neuromorphic computing. The second challenge is what we address in this paper. So this paper is basically, scaling down that neuromorphic chip. So you can, whatever I've showed you right now, this long-term plasticity, short-term plasticity, you can very well implement them using traditional silicon transistors, and it has already been done. So you can wire up a bunch of transistors, and you can implement a synapse that does both long-term plasticity and short-term plasticity. But what happens in the process of doing so is that you're scaling up the size of your synapse, right? So in the brain, we have around 240 trillion synapses. And if we take the approach of using the silicon transistors to do this, then it's not possible for us to even match that, right? Because at the end, the devices are super big. So in this paper, we show that you can overcome those limitations of big device footprint by having new types of devices. And this is exactly what we do here. We come up with a very small device, nanoscale device, that can substitute a micro scale transistor to do the same operation in a neural network. Yeah.
Just a quick question: the True North system, that's digital CMOS, right?
So not it's digital. I think the clock is digital, but you can always. I think you can opt no. So you can run it in the. I think in the Eleanor domain. So in the asynchronous domain as well.
Oh, interesting.
If I recollect, yeah. If I recollect, but nonetheless, there are plenty of other chips which are pure spike trains, asynchronous based. There's the Intel Lohi, there's Spinnaker, and there are plenty. You can just Google it, right? And there are also commercial products being launched. So there are a few startups that are making their own chips. But again, like I said, it depends what task you want to solve, right? If your task demands very high accuracy, then right now, with the current algorithms, neuromorphic may not be an option. But if your task demands energy efficiency, if it wants to work in the realm of milliwatts or microwatts of energy, then neuromorphic may be an option going forward.
If I can just, oh, go ahead, Serena.
Oh, no, go ahead. Go ahead.
Yeah, if I can put this in a bigger picture, we had here on Clubhouse. I don't know if you know Ronald Zuccarello, Miguel Nicolelis from the Blue Brain Project.
The Blue Brain, yeah. Oh, no, I'm not heard of this individual, but yeah, Blue Brain is quite famous.
Yeah, so they basically, like Ronald Zuccarello and Miguel Nicolelis, they said one of the reasons we couldn't have a Turing machine imitates a human brain would be because there wouldn't be a physical change or implementation of the memory or the processing that was back then. But I think your work and the other researchers working on this field are changing that. So there will be a physical implementation of information processing of the environment. So my idea is, just to give a bigger picture, my idea is that this will bring us closer to having a real AGI in the future. What do you think about that?
I think, yeah, I think we are bettering the technology that we have every passing day, right? Yeah, but I think so to be able to implement AGI is not just the hardware that needs to be investigated. It's also the software and the algorithms that you run, right? And there's a lot of there's a lot of research options at that end. So if one has to really make AGI, then there has to be research and improvements not only on the hardware side of things but also the software side of things. And yeah, one day we can potentially have AGI in the real world. Um, but just to again reinforce on the point that you said, right? So a lot of chips, for example, in the Blue Brain project or the Human Brain project, and SpinNec and whatnot, right? So they're still improving. Now and then they have different variants of the chip. So for instance, up until 2019 or 18, they were only working with synapses and neurons, right? There were no dendrites involved. Now they are bringing in the dendrites into the mix, into that chip, right? And this is happening. And if you have dendrites now on a chip, you can do additional computations with your hardware. And with the right algorithm, we can potentially implement AGI. Yeah.
I was curious, and I've been lately thinking about whether there's a connection here, and I'm curious what you think. The other aspect of research along these lines, getting away from von Neumann architectures and the current paradigm in AI, is the current work in SBIs. So people getting neurons in a dish, cultured neurons to learn things. I'm curious if you see that as an opportunity to learn, kind of rapidly iterate on what would work in a hardware implementation, or the way the input-output system would work for the hardware, whether there could be mutual inspiration there or not.
I think there's already some work along those lines, right? So this again brings to the example of DDS that we had. So you can have your cultured cells, neurons, and whenever they spike a train, whenever they spike an action potential, you can sense that action potential and transfer it to your silicon chip, right? And then learn based on the spiking patterns. So that's already happening in the field. Now, I don't think I'm educated enough to be able to claim that this is the way forward to doing this hybrid computing with brain and machine. But it's definitely quite interesting to look into, right? It sheds more light into how the neurons work. And at the end of the day, this is what we need on hardware. Yeah.
So I wanted to ask, we've been going for almost an hour and 20 minutes. So I want to be respectful for your time. How much longer do we have you for?
I think you can have me as long as you want. I think.
Oh, careful what you wish for.
Well, it's a Friday night, so there's nothing else to do. Yeah.
Okay, well, we can continue to take questions then. Nobody else? Do you have a question?
Not for now. It just popped in. Thank you so much, Lorena.
Okay.
I have one last kind of selfish question, and I'll stop asking questions. But I'm curious if you have any advice for anyone that's looking to get into this field. I had just in my case, I have an undergraduate in electrical engineering and CS. I was always stronger on the software side. In terms of electrical engineering, I was always thinking about signal processing. And I currently work in experimental, theoretical kind of, computational neuroscience. I'm just curious what skill sets are really required for entry into the field. And lastly, I kind of have this maybe a hoop dream in my head of there being this really tight integration with actual neuroscientific work. I'm curious how mistaken that would be to think of it that way.
I'm not sure if I followed your second part of the question. Neuromorphic. Can you repeat it?
So sorry, what was?
So the second question that you had.
Oh,
I
I was So the first one was just about what the entry point is, and then the second point was about how tightly integrated is this really with neuroscience? Like, is there
okay.
Yeah.
Right. So let me answer the second question, right? Because it goes with the flow. So it is intensively integrated with neuroscience. So, the Human Brain Project in Europe, the Blue Brain Project, they are the projects that, the most uh, funded projects, right, in the world right now. And they are funded because the idea is to understand and model the brain, right, um, with inclusion of neuromorphic chips, right. So they're heavily funded, right. Uh, uh, so there's the neuromorphic computing side of stuff that I talked about today, but there's other side where you want to test your computational neuroscience models, right. You want to validate if your theory about how the brain functions is correct, right. So uh, yeah, so basically neuromorphic computing emerged from this idea of uh, uh, understanding the brain on chip, right. So we first made chips that can that can implement the dynamics of the neurons. When we made them, we tried to implement computational neuroscience problems to do a bunch of things to understand if the brain functions this way or that way, right? And then we came up with the computing part. Hey, we have this hardware. Why not do some useful computation for the applications that we have today? So that's how things have evolved. So it is extremely tightly integrated, right? They are not separate fields; they're the same field. And this is one reason why neuromorphic computing is popular these days. It's not simply because it allows us to build better computers, but it also is because it also allows us to emulate the physical, biophysical mechanisms, and by emulation, test our hypothesis of the mechanisms in the brain. Yeah. So that's the second question that you asked. The first one, I think there are not really any specific requirements. So my background is just so you're already a step ahead of me, right? Just to let you know. So my background is in material science. I have worked with steels, with alloys, and now what I do is computer science, right? So all that takes really is the interest in the field. And one way to approach this field is if since you're a computer scientist, to try out coming up with new algorithms, for example, right? So you can read a bunch of papers in neuroscience, speculations to what the brain does, and perhaps use those ideas to come up with an algorithm that you can implement on a neuromorphic computing chip for some useful computational task. Um, yeah, so I think this is one way going forward. But there are ample opportunities, right? So algorithm side of things, there's also circuit side of things. If you want to build a neuromorphic chip, one has to be able to generate spike trains, integrate spike trains. So there's a lot of electrical engineering involved in this process. So yeah, if you're interested, right, then there are a lot of ample opportunities to grab on, and it will be an easy way in since you already have a background in computational in computer science. Yeah.
Thank you. Thank you. So it sounds like it's reasonable to have some neuroscientists or computational neuroscientists on these teams.
Oh, in my team. Sorry, I didn't get your question.
Yeah, in these development teams in general.
Oh, absolutely. No, so absolutely. I think the third author of the first paper, right? He is a computational neuroscientist. So he understands. For instance, he tries to develop models based on he tries to develop computational algorithms based on the models of the brain, right? So a lot of computational neuroscientists are actually doing AI right now, right? It's not a separate field anymore. They are intertwined in many ways. And what I mentioned, the projects like the Human Brain and the Blue Brain Project, it's not only involving neuroscientists, right? It's a mix of all possible disciplines. You have computer scientists, you have electrical engineering, material scientists. They're working together in building up hardware and algorithms. Yeah.
Well, okay. So we have some new people on stage. We can go in PTR order. White Hat, do you have any questions?
Yes, I have a question. See, I'm a solution architect, basically work in the fintech industry. I do programming in Java kind of technologies and design systems. So, I've been almost 20 years into the industry. But the question to Gussie is if I want to enter into this particular field because I'm very much interested to do some research on this artificial intelligence side and what we are speaking about like in a human mapping blueprint project kind of thing. So see I know I'm kind of probably not young enough to start everything, but if at all I'm interested where I can start which to some institutions or any training which I can
Oh,
start
right,
with.
right,
Yeah.
right. Right. Sure, sure. So I think there are a lot of job advertisements being posted now and then for different positions. I didn't get that about. I don't know what your background is right now in terms of your degree, but now and then there are ample opportunities being posted for computer scientists to jump onto the bandwagon. So all you have to do is, reach out to people and tell them what your skills are, and I'm sure they would be happy to have you, especially the computational neuroscientists, right? So to them, it will be interesting to have someone who can do computer science and implement some of the models they want to implement uh, on programming. Yeah, but there are ample opportunities.
I think
Uh,
yeah, I think I was late to join this conversation. So would you please let me know which country you're, I mean, if it is not personal, which project you're working on, where I can see this opportunities kind of thing, whether it's going to in Europe, US, or in Asian country, wherever it is.
Oh, right. So specific to us, I am placed in Europe. I'm in Switzerland, right? So I work for IBM Research in Switzerland, in Zurich. So you can always check out the website there. We have a good website where we post job openings now and then. And if it interests you, can reach out people. We have a team working exclusively on neuromorphic computing. And if they are interested, they will be keen to interview you. Nonetheless, we're not the only one, right? Like I said, Europe is heavily investing into understanding the brain better, into building AI chips. So you should be more open to looking into opportunities uh, in multiple places within Europe, for example. Yeah.
Oh, Kyle, do you have a question?
Yes, just quickly. My question is in relation to the chip shortage that we're experiencing. I was wondering if you could touch upon that. I'm wondering if the innovation is lagging behind the availability for chips or the other way around.
Ah, right. I think it does. So for instance, we have had the first-hand experience of this. So if you really want to build up a scaled up chip, right? Uh, so what we did in this paper, it's not a chip that would go into a product. It's nowhere there, right? It's a proof of principle demonstration in the papers that we have. But if you want to build up a full-fledged chip, then it has to go through a foundry, a semiconductor foundry, and there, this is where this chip shortage comes in. You are delayed in getting your chip back to be able to do useful research or to be able to do productization. But nonetheless, what we do and most people do in this blue brain project, or they work with indigenous chips, right? They're not working with the cutthroat process of making devices and wafers. They are working with older generation of fabrication technologies and older variants of silicon. So they can still tweak with, they can still, they can still research. It wouldn't impact them the way you think it's impacting right now the commercial market, for example. Yeah, it definitely has an impact, but in research where you are doing more of an exploratory science, the impact is not severe. So that is how I would put it. Yeah.
Okay, Rabbit, and then we'll go to Abyss.
Hey everyone, how are y'all?
Did you
Hi.
have a question?
Yeah, I studied in graduate school. I studied genetic algorithms with structured data, advanced data structures, underneath my professor Zbigniew Mikhailovich. He has a book that's called Genetic Algorithms plus Data Structures equals Evolutionary Programming. And I also did some work on neural networks like 2-layer and 3-layer networks. And back then, we adjusted, sometimes using genetic crossover and mutation to train the neural network by modifying the weight of each connection in the network. And so part of my question is, do these neuroplasticity chips that you're speaking about still model the synaptic relationship between two neural nodes as merely a single weight versus a more complicated synaptic model like we see in the brain, because there's this new discovery of the importance of what are called astrocytes. So, to continue briefly, what I'm saying, any flow network, whether it be electricity or petroleum or any sort of flow network, requires the presence of a control network that is kind of symbiotic to the flow network. And the control network adjusts the flow. And so, in that sense, perhaps the synaptic connections between neurons is partnering with the astrocytes, which modify the secondary and tertiary neurotransmitter emission within the synapse, which either elevates or reduces the strength of the synapse, modeled more sophisticatedly than merely a number of weighting. So I was wondering about control network and modeling a more sophisticated synapse. Thank you so much.
So thank you for the great question, and your research and your professor's research sounds quite fascinating. But I must confess that I am not capably educated to be able to speak about this flow networks and the new model that you're mentioning, right? It could well be that this is what happens in the brain, and if it does happen, then in the future we may come up with a device or a way of implementing this on the hardware. And this is what we do right now with our chip. Traditionally, it was thought that it is only the long-term plasticity, the weight that needs to be that is the only thing that is needed to implement neuromorphic computing, right? But like you said, there's more sophistication more complexity to the synapse than we think there is. And one complexity is the short-term plasticity, and this is what we address right now in our research. There could very well be other mechanisms that determine the state of the synapse, and yeah, and maybe someone will do it in the future.
Yeah. Sorry.
Yeah, you're right. So the overarching the takeaway message of my talk today is exactly what you're trying to claim. There's more complexity to the synapses, and if that complexity can be emulated on hardware, then one can perform computations in a more efficient way. But what mechanisms dictate that complexity that have been uncovered every passing day, right? In a way.
Yeah, great. One of the aspects of the astrocytes was the control of emission and uptake of potassium ions, which affected the electrical conductivity across the synapse. But there's
Right.
also secondary and tertiary neurotransmitters, which also modify the effectiveness of a synapse.
Right.
Yeah, so it's
Right.
all very, very interesting.
It is. So one mechanism for short-term plasticity, right? It's again in the line of what you mentioned. So one possible mechanism for short-term memory or short-term plasticity is the uptake and intake of magnesium ions, for instance, right? Or calcium ions. So it's along the same direction of what you mentioned right now. Yeah.
Curiosity would be, is it directly proportionate with the amount of, let's say, sodium in the system? Because usually potassium counteracts sodium.
Um, right. But I think right now we're talking about right. So what dictates the action potential at the synapse are not just the concentrations of your primary ions, sodium and potassium or calcium, right? It's also the neurotransmitters that you have, right? So the synaptic strength in a way is also a function of your neurotransmitters in addition to the ions. Um, yeah. But definitely, yes. The ability of your neuron to generate action potential depends on your membrane potential, right? In a way, and that is dictated by the concentration of your uh, ions. Uh, and this is where the idea of homeostasis comes in, right? In homeostasis, in homeostatic plasticity, you're modulating the medium in which your neuron is. You're essentially modulating the number of the concentration of the sodium ions and the calcium and the potassium ions, and this has consequences on how the neuron fires or behaves.
Yeah, my limited under
Okay,
my limit.
let's go to Abyss, and then I'll
I just
after this
I just had
I have a
one thing
well
to
I have
add.
so let's go to Abyss, and then I have a question to follow up on astrocytes because that's a fascinating topic. So
Yeah, it is.
I also have a question. I'll wait for my turn.
okay, Abyss, what's on your mind?
Hi, Serena. Hi, Kat. And hi, Gizzy. Uh, I'm sorry if I say
Hi.
your name incorrectly. Yeah,
Speak up a bit.
great presentation. Can you guys hear me all right?
Yeah.
Okay. Yeah, so yeah, I came in late to the presentation, but I'm really fascinated. I've been fascinated with neuromorphic circuits for quite some time now. And I'm taking it like I'm gleaning through the paper and I'm looking at really fascinating findings. I do have a couple of questions for you. The first one being that I guess like Wisdom also touched upon this earlier, which is the computational neuroscience is kind of evolving in a way. You don't, I mean, the type of firings that each unit actually responds to is highly dependent on the neurobiology of the neuron itself. So I'm just curious like how the neuromorphic circuits are capable of adapting to a new kind of computational model that kind of mirrors the biological system. So I'll start with that one.
Right. Yeah, that's a good question. So, right. So I mentioned a few times this EU-funded project called the Blue Brain Project or the Human Brain Project, right? Now they have come up with a list of uh, the complexity of abstraction, right? So you can approximate your neurons to various degrees, right? It can be a very simple threshold model, which does not take a lot of space in a lot of data, right? Or it can be very complex. You can have all your ion channels involved, your medium involved, and then it takes a lot of data and it makes it very energy inefficient. So to answer your question, yes, there are different models that one can implement on a chip to capture the different complexity of a neuron. But the more complex your neuron model becomes, the more processing you need on a chip. So that's where the complexity comes in. I think if you want to just make a threshold neuron model without ion channels and whatnot, just to put into perspective, you're working with kilobytes of data, right, to compute. But if you now include ion channels, if you include different mechanisms and whatnot, then it jumps to megabytes and gigabytes per neuron, right? You're talking just one neuron. The data transmission is one neuron. So it becomes extremely complex. And you're solving on top of the differential equations and whatnot. So the complexity increases as you try to model your neuron more and more rigorously. Does that answer your question? Did I get it right?
It does actually. Like you also address the concern that modeling a neuron is not an easy task. I mean, basically, you're dealing with a bunch of differential equations, and simplicity itself is required in order to mirror that. Um, activity so that you can create a very efficient neuromorphic neuron. So thank you for that. The second question is probably, the last one is that I think Kyle also touched upon this, that is there a way to kind of go from like the FPGA kind of modeling where you test out different neuromorphic computations to creating like stamping like a CMOS that's kind of dedicated to doing certain kind of computation for specific tasks, or even MEMS device that are kind of fine-tuned to doing specific computations. Is there I guess that my question is like, is there a way to go from like the prototyping phase to the product shipment phase where you don't have to rely on silicon wafers, but instead you can try out other kinds of computational materials to perform neuromorphic circuit or to neuromorphic computation?
Oh, absolutely, absolutely. So, FPGA is heavily involved these days. You can basically make a neural network using FPGA, and there are platforms that are purely based on FPGA doing what a silicon chip does today, right? And yeah, so basically, you should think of a neural network as a black box, right? You input something and get output. You get an output of something, right? What hardware you use in the black box really depends on what application that you are trying to work with. But FPGAs are quite popular in the field of neuromorphic computing and in neural networks. The second question was, if I got it right, specialized chips, right? So right now, machine learning runs on specialized chips. So for example, the AI that happens on Google, it happens on a chip that's called tensor processing unit, and there's a specialized chip that is meant to do matrix vector multiplication operation. It's only for that, right? In Tesla, right? So Tesla has its own, smart cars and autonomous driving. They have made their own specialized chips to do AI tasks, right? So just as a disclaimer, right? Tesla is not a chip making company. Google's not a chip making company, but they have started to make their own chips, specialized chips, to
including
implement.
Google.
Yeah, including Google, right? Google, Baidu, Amazon, right? Whatnot. So they're making their own specialized chips, proprietary chips to implement their workloads. So yeah, specialized chips is how the things are right now.
Dr. Sarwat.
But there's a
sorry.
yeah, sorry, go ahead.
Okay,
But there's a downside to specialized chips, right? With the specialized chips, you become extremely narrow, right? And with a specialized chip, you never will be able to, get to a stage where you can implement AGI that we were talking about a few minutes ago. So it's also important that the network is flexible, or the chip is flexible to be able to do other operations. Yeah, sorry, go ahead.
So I wanted to, and thank you. I wanted to bring it back to astrocytes because it's such a fascinating topic, and the neurobiology of what we've learned in the last decade is exploding, and the implications are profound for these. Certainly, to follow up, Rabbit and nobody else, in the mentioning the tripartite synapse, where regulation of the synapse is a fairly active process, and we're understanding much more about what goes on there. Certainly in the sense of isopotentiality of potassium regulation, but also in terms of the astrocyte networks, and in particular the astrocyte syncytium. The astrocytes themselves form gap junctions and extended non-local networks, and they reach out through fine processes to interact with many synapses. And
Absolutely, yeah.
as they become activated, they set up resonances in calcium oscillations, which extend over large periods, and are thought to bring many neurons into synchronicity. And so in terms of the research challenges of modeling that, I mean, astrocytes can move around, they can change their morphology, and they if their interesting function is in terms of building up and sustaining, in essence, integrating in the form of calcium oscillations that contribute to theta wave frequencies. How might we model that in terms of hardware? And that's a very difficult challenge.
Right,
Um,
right, right,
Can I
right.
also
So,
squeeze my question in there for a second? I think it could be
yeah,
related. I think it could bring it back together, and then
sure, go ahead.
maybe Dr. Sarwat.
sure.
Dr. Sarwat, if you could bear in mind the previous very prolific comment and question, Serena, and also if you could talk a bit about like your thoughts and your knowledge on companies like Kernel. You know, Brian Johnson works on this brain-computer interface that is non-invasive, that picks up on those specific frequencies. Let's say, like a
Mm-hmm.
like an Apple Watch, for lack of a better comparison. I'll stop there. But if you could, like, it could make a lot of difference discerning between what is circumstantial in terms of problems, um, mental illness, what is acute, what could be circumstantial. I'll stop there. I'm sure you already know about the.
Right, right. So I think both Saina, you are going to be disappointed with my answer, but to be very frank, I'm not very familiar with astrocytes, right? And the mechanisms that they result in. Nonetheless, what we have discussed so far are the traditional emulations of neural networks, right? Um, uh, there are hardware emulations that are based on oscillations. So you can build a neural network on hardware that is purely based on oscillatory processes, where the output is dictated by the differences in the phases of the inputs. And I think there may be an opportunity where this idea of astrocytes can be tried. So there's always, I think, yeah, something to think about there. So yeah, so I think
For
so
example, if
that's the
yeah,
best I can answer with to your question. So yeah.
I mean, it would be so in terms of theta waves, that's it's up like 5 to 10 hertz. But in terms
Right.
of your spike train, they were your device was down in the nanoseconds, right? Periods.
Oh, right,
Is
but right. Now
so
this is
just
where the distinction between right, go ahead. Yeah.
so I was just curious, like in the example with the reward function implemented in terms of light, if there's an emergent type of temporal correlation that
Oh,
could drive lower frequency oscillations that would select in temporal periods, for example, at much lower frequencies. Perhaps that could drive synchronicity in these larger circuits, for example. Not necessarily trying to model the whole astrocytic network, but at least some aspects of the functional behavior of
sure,
transferring to lower frequency resonances to condition groups of
sure.
neurons. Hmm.
Sure, I think it can very well be done. I think it all takes a clever idea to come up with a device that can implement this, right? And if one puts thoughts into it, I'm sure there would be a hardware that can emulate this networks that you're talking about.
Yeah, if I
But
can, if I'm
like I said, there are already different approaches to implementing a neuromorphic chip. So there's an entire field of oscillatory neural networks that can synchronize, where neurons are synchronized with each other, just like what you said, that this could potentially be implemented. Yeah.
Yeah, so if you would look at Dr. Pascalis
Mm-hmm.
Goupidenis,
Yeah.
he was a guest speaker here before. He is at Max Planck Institute. He
Yes.
did this, and I shared the paper for the audience or anyone who's interested. I shared it in the chat, the paper. You can
Oh, that's
also check
awesome.
out the recording. Yeah, he did this work about functional connectivity of these devices and having global voltage oscillations that are
Mm-hmm.
comparable to actual brainwave networks
Yes,
organoids are being.
yes, right. I'm very aware of his work, and you're right. So what he and his team are trying to build are these devices that work with, these are organic devices. You're using polymers and whatnot, right? Um, and so it's more of an approach where you're trying to build models to implement the mechanisms of the brain. What I am doing and my team is doing is that we are building chips based on inorganic materials, meaning that we are really interested in making a technology that can be used by you and I, right, at the end of the day. So there's a big difference there, right? But nonetheless, any idea there is in neuroscience with proper thinking and expertise, it can be implemented on hardware. This is what I've learned so far in my experience, right? Um, yeah, good.
Yeah, thank you so much. And I'm aware you have to leave. So I wanted to give you the opportunity to get rid of us on your
No,
Friday
thank you.
night. No, thank you so much for being here and answering all of our questions so patiently and giving this great talk and this opportunity to talk with you. Your research is very interesting and important and lead us into hopefully a great future and saving a lot of resources. So thank you for that. And you're always welcome back to come back with maybe updates on your research that you're allowed to share if you're interested. So yeah, please come back anytime.
Sure. Thank you very much for having me. I'm humbled by your invitation, really. And like I said, this is a new experience. Uh, I've never done a telephonic discussion this long before. Yeah. So yeah, I think I learned things as well from this discussion that we had today. And I hope, and I really hope that I was clear in my language and in my tone, that the message I wanted to pass was delivered. Right. Yeah. Good.
I just wanted
Thank
to
you very
chime in
much.
on thanking you for spending time with us. This has been really enlightening and inspiring for me. So thanks for your time.
Thank you.
Thank you
Thanks
very
for
much, Doctor.
listening,
You've
for
covered a lot
joining.
of amazing things. Thank you so
Thank you
much.
so much.
Thank you so
Yeah,
much.
I
Yeah,
started
thank
Welcome.
at
you.
the
Thank
beginning, but
you
this was
so much.
great. Enjoyed
We
your.
should
Yeah, we
Hope to connect
recorded
again.
the session, so you're invited to record. And maybe if you have questions, we either have a weekly recap on Monday this time, not on Sunday, where we summarize and answer questions that you might not have a chance to ask this time. And then also you can email me or direct message me with questions, and maybe I can maybe forward them if it's something I cannot answer
Sure.
myself. So yeah,
Absolutely. Thank
thank
you.
you so
Oh,
much again.
I
Enjoy
think
your weekend.
you
How's the
too.
weather in Switzerland? Is it okay or rainy like
Oh
in New
no,
York?
it's terrible. It's
Oh
terrible.
yeah,
Don't
the spring is horrible.
it's terrible.
Everything is
Oh,
melting and raining and snowy.
yeah, it's very rainy. That's true. Yeah. Out
You
of
have to go
curiosity,
up
right?
to the Alps too. There are spots where you can ski and this time in a t-shirt basically, but it's high up, so there's still enough frozen ice. You should check it out.
Right.
Betma
well,
Alp
well,
is
you
a
should.
great spot.
well, you should know that I'm not Swiss. I'm Indian. I'm sure to break my bones if
Oh
I
yeah,
ski.
they have great teachers. they they have great teachers. I can recommend you
Sure.
to go to
What was your
places.
curiosity, Dr. Sarwat?
Right. So I wanted to. I think I really like what you people have done. Right. It's very interesting that a bunch of individuals came together to create this forum. I was just wondering if you can tell me briefly how it came about and what your intentions are going forward.
So yeah, thank you for asking that. That's really nice. So actually, I came onto this app mostly during like COVID times, and then people start asking me about my work, and then I kind of was boring just to talk about myself. So I started inviting people, other scientists, and then I did this club, and now it became a really regular thing, like almost every day. And and it's been great that we have really great experts coming, and we're making great connections. And I'm planning the next step would be to invite maybe groups of the different fields to discuss together. So maybe if you're available in the future, maybe in the fall, I would invite you and Pascalis to talk about this maybe together, maybe with a few other people. And then we'll go from there. Like I made the actual organization out of it. Hopefully we'll one day expand more and have a physical place also to have people connecting. So yeah, let's see. But for now, I'm happy with how it's working out.
Okay, that's very cool. That's very nice, and well done on what you have achieved so far. And yeah, all the very best for your ambitions of making this an independent platform. I think it'll be a great service to science, right?
Yeah.
All the very best.
Yeah,
Definitely.
it's to give people the availability to learn about science from the people that actually doing the science. And I think we learned a lot. I learned a lot. I never learned so much in my life, because I
Clubhouse
have to read
master's
all these
degree.
papers every day.
Yeah,
You should put that
Dr.
on your
Sarwat,
bio. I have a
Katerina.
Clubhouse master's degree.
Right. I just wanted to add, Katerina gave a very humble summary. The Science Society is growing very quickly, and it's because of the content that and the speakers and the quality that Katerina brings. And she's really done a fantastic job, and we're growing very fast. So it's a wonderful experience. And if when life sort of takes you away for a few days, you really miss it. And it's great to come
We're
back
proud
to
of
have
you,
True, that's
terrific
Katerina.
true.
content.
Well done, you. We're proud of you.
You have amazing teammates, Katrina.
Yeah, thank you. Oh,
That's
I'm
good.
humbled. Thank you. I would be nothing without all the help and everyone being
Yeah,
here.
yeah.
So
All
Well,
right.
so
thank you.
I
oh,
honestly,
go ahead.
I honestly have no idea how you do it, Katerina. I don't.
It's amazing.
I'm like loosely committed to a one room a week, and I feel like I don't know. Anyway, good. This is great.
Well, and so
I'm
just
I'm
as
in,
go ahead. Sorry.
I was going to say I'm intrigued by the possibility of going skiing this time of year.
It's wonderful. It's the best time in Switzerland to
Uh,
ski is
I'm more
now.
of an
It's the best
I'm
time
more of an
because there's not this cold storm. If you high up, as I said, the ice is still like the snow ice is still there. If you're at like 3,000 something meters,
yeah.
and there are villages where you don't have any cars, so you have to take this cable things to come up there, and there are small villages high up, and there's no traffic, nothing that disturbs
Yeah.
you.
I've
Glacier is close by. It's amazing. It's the best place
I've
ever.
skied St. Moritz, Zermatt, Interlaken, but I'm more of a fan of the Austrian glaciers around Innsbruck. It's called Stubai Glacier.
Yeah, I've been there too. But Betma Alp, check it out. It's so silent. You don't experience that anywhere else. The silence combined the snow with no traffic and like I don't know for how many miles around you.
Exactly,
It's
and
amazing.
I feel like the same problem exists with noise. Sorry, with light pollution. It's getting harder and harder to observe the cosmos in the backyard with a
That's
telescope.
what she said.
Yeah,
Well, I thought she was talking about
yeah. Also
noise.
No, it
noise,
was a
but
joke. It was a
light
joke.
also. Yeah,
Oh,
no,
okay.
no. It's yeah, you're right. Also the light is it's amazing, and yeah, it's a wonderful place, and the milk from these high up cows are the best. They bring the cows up to the Alm in the summer, and so they get this special grass with all these different flowers that the milk. I don't like milk, cow milk, but there I love cow milk. Like it's not processed; it's just right out of the cow. Basically, it's amazing. Anyways, and the chocolate, like everything is amazing. Basically.
Well, that's very true. All right.
Okay, great. Enjoy your weekend. Thank you everyone for coming. Follow the club if you enjoyed this. We'll have more rooms next week. And yeah, thank you so much, Gazi, and wish you all the best for your research. And thanks for
Thank
coming
you.
again.
Likewise. Take
Thanks,
Wunderbar,
care.
everyone.
wunderbar. Eshtayaba.
Thank you very
Ciao,
much.
Wunderbar.
Bella.
Ciao.
Ciao.
Bye,
Bye.
everyone.
Goodbye,
Aloha.
Bye,
everyone.
everyone.
Bye.
Bye, everyone.